Okay, good morning, everyone. My name's Paul Baker from Glasgow Caledonian University, and I'm a building physicist. I'm going to give an introduction to the LORD software, which will be available for downloading. I'm also going to look at some examples of data analysis using data sets from PSA in Spain from their test box, and that will also be available. I'm also going to look at some steady state analysis, which are the methods are suitable for obtaining preliminary estimates of whole building thermal transmittances and solar apertures. The origins of LORD, it was developed for the PASLink projects by Olaf Gutzke of BTU Cottbus in Germany to analyze dynamic test cell data and deliver high quality performance characteristics for building components tested in real climatic conditions. So there were a number of test cells distributed across Europe, and a number of European projects were carried out, mostly looking at the passive solar components, and it was found that people started off using fairly steady state analyses, which proved to be inadequate, and gradually more dynamic methods of analysis were introduced. So LORD can be used for analyzing components such as windows, walls, etc., and whole rooms or more complicated systems. It's basically used to obtain thermal transmittance values, solar gain factors, and possibly dynamic information such as capacitances and time constants. A transient mathematical model is assumed. The parameters of the model, such as resistances, capacitances, and heat flow admittances, essentially define the dynamic and steady state thermal and solar properties of the system. LORD basically uses RC networks to model system. So the program makes, once you've created a network, the program makes initial guesses of the parameter values, and the output of the actual test, for example, the test room temperature as a function of time, is compared with the output which the model produces for the same input conditions. And by statistical analysis of the deviations between the model and the measured outputs, the parameter values are progressively adjusted in order to improve the agreement. I suggest that you read the LORD manual and the other documents provided. It has a, well, mostly use friendly interface. Step by step, first of all, we need to input the data. So you open a data file, which will have a time series, different columns representing the different variables, and you can basically add all or just some of the variables into the project where you will create a network. File formats are quite important because often people have suffered problems from, for example, the header is not quite right. So headers must be enclosed in single quotation marks, and the data can be tab delimited or comma separated variables. The second step is to create a model. You basically connect the nodes in the model, and that produces conductances, and you can set these to any value you like, and they could be fixed or variable, but usually the conductances you set as variable. And when you have connected the nodes, you'll see that capacitances are given for each node. Usually at the internal and external nodes, you set the capacitances to 0. The default time step is 60 minutes, but make sure that if you're using 10-minute data, you adjust the time step in the model accordingly. So often we start off with a relatively simple 4-node model. For example, if we're looking at heat flow measurements through a wall. To this model, we need to link the model to the data. So this is the third step. So we go to the link data to nodes tab in the software, and we select the temperatures and the heat fluxes. So here we have an example of, we have the test room with an external surface temperature at the back of the room, which is connected to node 1, and we connect the corresponding internal surface temperature to node 4, and also at node 4 we connect the heat flux measured on the wall. Now we go back to the model, and if we're using heat flux, or for example in a whole building you would have the heating power, the aperture for these is fixed at 1, because essentially the heat flux is a fixed amount. of energy going into the wall. But if you're using solar radiation, we don't actually know. We have maybe a solar emitter that's measuring solar radiation in watts per meter squared, but we don't know how much solar radiation is actually influencing the performance of the building. So we have a variable aperture. And in the model page, you can also, well, you have to select an output, which is the variable that you're essentially using to determine the result. So here, for example, I've selected the heat flux, but often you can also use the internal temperature. It is possible in Lords Connect to use more than one output, but it would be unusual to do that. Step 5, we need to set the interior and external nodes. So, for example, in our case, the interior node where the internal surface temperature is located is the interior node, and node number 1 where the external surface temperature is located is the exterior node. If you were measuring solar radiation, you would also specify which variable was the solar radiation. But in this example here, we're just looking at a fixed heat flow, and we're not looking at measured values of solar radiation. Originally, as Lord was meant for looking at the whole thermal transmission values for a test cell, it calculates a UA value. But when we're looking at 1D values, then we're actually looking at U values and G values. You can set the initial conditions for the model. So you can either fix the starting temperature for the nodes at a value that you can input, but it's preferable to use the option of identifying the startup temperatures like variable parameters. There's a third option, which is let constant at their actual values, and I'll talk about that later. There's also the option to set limits of the parameters so that you can either have them completely free floating, although you can run into problems because that you can sometimes get the values sort of running away to ridiculous numbers. So one tries to set them within a reasonable range of values. So that is really where the sort of experience of the user comes in. you're allowed to use either the output error method or the prediction error method. But generally speaking, we'll use the output error method. Although using PEM, you get smaller residuals than using the output error method, but the identification process takes much longer using PEM, and PEM can only be used if the outputs are measured temperatures, and often it's preferable to use heat flux as an output. I suggest asking a statistician to explain the differences and benefits of using the different methods. There are other functions that you can use. So you could create, for example, a variable resistance which depends on a measured parameter such as wind speed. For example, if you were measuring the whole house thermal transmission of a real building which had a definite air leakage, it might be that it would be useful to create a resistance, or rather conduction value, that was actually a function of wind speed. But generally speaking, it tends to complicate the model somewhat, and it's worthwhile if you go down the route of creating a variable function, that you compare that with the results from a model where you've just used fixed values for the conductances, and see if there is any improvement at all. Lord has a facility that you can use fitting windows. So you look at the output graphics, and by the fitting window is that yellow window there, and by right-clicking on that window, you can adjust the data that you're looking at, and it's possible, for example, to have more than one fitting window, and the Lord manual gives you instructions to do that. So, for example, if you had a data set where you identified that at some point there was a problem with a sensor, you could isolate that and just look at the data either side of that problem. But also you can actually introduce a daily pattern to the data. So, for example, if you were carrying out heat flux measurements on a window to estimate the window U value, you could just select the nighttime data. So Lord has a facility that you can decide at what time night starts, and then when the day begins, and so you can exclude the solar radiation data. this may be useful for looking at other situations. For example, Hans showed the problem with solar radiation hitting or a heat flux sensor responding to the solar radiation. Now, if you just looked at the nighttime data, you could maybe get some useful results by excluding the solar radiation in that situation. With windows, it's more justifiable, I think, because the windows generally have very relatively high thermal conductivity and low thermal capacitance. So the influence of any solar radiation on the window dies out quite rapidly. So if you use the nighttime data, I think you can justify using this approach, and you can get reasonable results. So then you run the model, and you'll get in the output screen the graphics show the bottom of the left-hand slide shows the measured and calculated results. So it looks like you get quite a good fit there with this particular model, although the upper graph on the left-hand side shows the residuals, which are not fantastic. They're certainly not white noise. So maybe we need to have a better model, or there are unknown factors that we can't account for. And the screenshot on the right-hand side shows the results for all of the parameters, and the overall U value, and in this case the G value was not calculated. That you get a confidence limit for the calculation, which is usually quite small. It's useful to, which I'll go on to speak about in a minute. You know, is this value that we're getting of 0.496 watts per K a realistic value for the data? You get two forms of output file. First of all, the log file gives all the input and output information, including the results. And statistical information generated by the program. The res file gives the measured and calculated values of the output variable. So in this example, we can see there's reasonably good correspondence between the calculated value and the measured value. So if the next stage is, if you're satisfied with the model, save the model for future use. And there's a final option in LORD which enables you to carry out an error analysis. So essentially, you can input the uncertainty on the measurements, and it calculates new values of the parameters perturbing the inputs by the uncertainty. And so it will give you a result with the undisturbed inputs and the total error, which is a root mean square value. So this is quite a useful facility, because I think you should always give some uncertainty value due to the measurement uncertainties in your final value. We can also use LORD for simulation or validation purposes. So I've used as an example here the data that will be provided from the PSA test site, and there's a series of data, series 16, 17, and 18, which is a continuous series, but each part of, for example, series 16 has a random heating sequence imposed. So it's a very, very dynamic data, whereas series 17 and 18 are more steady state. So in the example here, I've run LORD for series 16 only to get the parameters from the dynamic data. So I obtain the results and save the model. And then I go back through all the parameters and settings and fix all the parameters and set the initial conditions to their actual values. Otherwise, even if you fixed everything else, if you, for example, left on the identify like variable parameters, it would really allow things to start recalculating the parameters. So then we go to our graphics output tab, and we move the window over to series 18, and then we run LORD again. So when you run the simulation, you will get a information screen like this, where it will say there are no variable parameters, therefore the calculation was done in the simulation mode, which is only one run. So here we are. So I've used series 16 to get the initial results, and then I've applied it to series 18. So there's a reasonable fit, but there are some areas here where there's a definite discrepancy between the measured and calculated. But generally speaking, series 16 results give a reasonable fit to the rest of the data. You could also use a completely different data set and transport the model and run the model that you've generated for series 16 to another data set from the same environment. Now we'll look at using LORD and its application to real data. Firstly, as Hans has mentioned in his presentation, you must process the data and check the integrity of the data. Use graphical plots to observe whether there are any problems with the data. Are any data missing? Are there any anomalies that you think there's an unusual spike in temperature? And for example, the PSA data is at minutely intervals. What is the best data interval to use? And I'll give an example of using the PSA series data where you've got the minutely data, but what is the optimum data interval in order to not lose the dynamic information? I mean, you could use the 1 minute data, but there's maybe too much information there, and that could result in too long a computation time. For example, in series 16, the graph below, there's a randomly ordered logarithmic binary sequence applied, and it's based on 30-minute periods. So the maximum interval to include all dynamic information is 30 minutes. So it could be better to use 10-minute averages. So as a practical example, you first of all need to look at the data and check to identify the start of the heating sequence. So we found here that the sequence changes on the hour or the half hour. Therefore, start averaging at the beginning of series 16, which starts at midnight. And so this then you ensure that you capture all the dynamic information. The following figures show the effect of different averaging periods. 10 minutes, 30 minutes, 1 hour, and 24 hours. So on the top left, here we have 10 minutes averaging, top right, 30-minute averaging, but you don't see that much difference between the 10-minute and the 30-minute average data. But when we switch to hourly averaging, you can see that you lose quite a lot of the dynamic information, and if you just use daily values, then essentially you've lost probably most of the dynamic information, and you certainly wouldn't use daily averages in a program like LORD, although you might use hourly data, and in fact often data series, the examples that you've been given for downloading, usually you'll look at hourly data. But here you can see that it's probably better if you use a smaller time step, 10 minutes or 30 minutes. Here we have the previous slide showed the heating power, and here we have the solar radiation. You can probably see here that you probably retain most of the information with 10 minutes, 30 minutes, and hourly data, and then daily data, then you tend to lose the information. And here we have internal and external temperatures. Again, if you use 10 minutes, 30 minutes, an hour, that's quite okay. But again, with daily, you lose that dynamic information to some extent. Similarly, if we look at the surface temperatures. Again, with heat flux measurements, you can also see that you certainly, with 10-minute data, you can see much more variation in the heat fluxes compared to 30 minutes or hourly data. And certainly you lose the dynamics when you're looking at daily data. When we apply LORD to the heat flux measurements from the PSA data, it's helpful to get preliminary estimates by simple averaging before running LORD on the data. And here I've tried 3 approaches using the different temperatures available for the internal environment, because we're given a sort of a single spot reading of surface temperature, a group of temperatures on a surface, and also a temperature that's associated with the heat flux sensor. So these results will give you a good idea of what the U value results should be like when you use LORD to identify the values. So I've used well, the rear wall and one of the other walls actually as examples, and we use the basic 4-node model, which is generally satisfactory for this kind of analysis. But again, it's up to you if you're going to use LORD to experiment with maybe a 3-node model or use more, but generally speaking, a 4-node model works well. So in the examples here, I've used the external surface temperature, and for the internal temperature, I've used there's a PT100 temperature sensor because it's more local to the heat flux sensor. I've tried the average surface temperature over the area of the wall and the internal room temperature, TI. However, the PT100 temperature produces better results with lower residuals. So here are the examples of using the different temperatures. So the top left-hand slide shows TSI used as output, which is the temperature associated with the heat flux meter. The top right-hand slide shows the results for using the average surface temperature for the wall, and you can see there that the residuals are quite high, and similarly, if we use the air temperature as output, there's also quite high residuals, probably because there's stratification in the test room. So TSI appears to give the best fit. I've also shown here examples using the fairly steady state series 17 and using different averaging periods, and actually you don't really get very much difference between the different hourly periods or the averaging method. So here we can say that using the hourly average data actually improves residuals, as you tend to smooth out the more extreme spikes, but it might also be useful to improve the model. for example, try using the heat flux as the output. I'm going to now look at using identifying values for whole test cells, which could be, or for actual co-heating tests of a real building where we're interested in the whole room or house thermal transmission values and solar gain factors. So for heat flux measurements, we can easily get an idea of the U value by the averaging method, but this is not possible for UA and GA values. Essentially, you cannot easily identify the heat loss or the solar gain factor of the building envelope directly. But we can make an estimate using the daily average data with Siviour analysis for the data series, and I explain Siviour analysis. We basically use daily averages or longer, and basically you use the equation where the heating power is the UA value times the temperature difference between inside and outside minus the GA value times the solar radiation. And if we divide through by delta T, you essentially get the Y variable is the heating power divided by the temperature difference, and the X value is the solar radiation divided by delta T, and the intercept on the y-axis gives you the UA value, and the slope of the line by linear regression gives you the GA value. So if we look at all the data, daily data from series 16 to 18, there's quite a lot of scatter, but it's actually giving what we know to be a reasonable value of the GA value, not the GA value, the UA value of 4.1. But now if we look at the data from each section of the data series, we can see that series 17, which is the best sort of steady state data, you get quite a good correlation of 0.92 R squared, and I think we get reasonable values also of the UA and the GA value. So it does suggest that this series would possibly give results for, certainly for the steady state parameters. But it's a good starting point in terms of guesstimating what kind of result we should be getting. Here are some research papers on co-heating tests. which usually these steady state methods are used, and this kind of Siviour analysis or possibly multiple linear regression methods are used. One of the papers concludes that, particularly with variable weather conditions, heat gains from solar irradiance were the largest cause of uncertainty in the test results. And you can see, because there's often cross-correlation with steady-state tests between the UA and the GA value, that the actual steady-state test method causes problems, and through the PASSES and PASLink projects, then it was a lot of effort was taken with the test sequences to actually decorrelate the solar and the heating inputs into the test rooms. You can use multiple regression and also get a reasonable result. So you treat the GV and the delta T as independent variables. You could adjust the daily values of heating power for solar gains. So you can get a plot really where you just measure the slope of the line. But I think this approach is only useful if you're really interested in just the UA values. So in LORD, the model gets a bit more complicated with when you add solar radiation. For example, this model, I've put in an additional parallel conductance between node 2 and 5, which allows for thermal conduction without storage, i.e. a window. And I've added apertures for solar radiation hitting the outside and also the inside of the room. But you can actually simplify this really by eliminating one of the GV apertures and even eliminating the additional parallel conductance. It's just a case of trying out these different models and seeing what you get. So here we are looking at different averaging periods on series 17. And one thing that emerges here is that if we run the model just on series 17, you get a pretty poor fit to the rest of the data. And you get a much better result if you use the more dynamic series 16. So I expected anyway the more steady state series would give good results. However, it tends to give high values. Also, the fit to the model to the rest of the data is pretty poor. So 16 seems to give better results and an overall better fit to all the data. Do we use 10-minute or hourly data? And also, are there problems with higher frequency data using LORD? Try a different model. So finally, it's important to understand the physical system. For example, the construction of the PSA test cell and the sensor locations. Plot the data, check for integrity, use simple averaging or Siviour analysis to estimate results prior to using identification techniques. Select suitable data averaging periods, particularly the dynamic test sequences. Compare different parts of the test sequences. And finally, please note I've not even mentioned capacitance yet. Thank you very much. Thank you for your attention.